Empirical formula, notes page 94, example 3 is based on an hydrate. Reading through the given problem, determine the number of water molecules, which is represented by N. If you take a look at the bolded hydrate formula, NaCl, big fat dot, and instead of a number in front of the H2O, there is an N. So our job is to figure out the value of N, what number should go in front of the water in the hydrate. So determine the number of water molecules in hydrated sodium chloride if 45.00 grams of the hydrated salt is heated to a constant mass of 27.86 grams. Complete the hydrated formula. So even though this sounds very different, this is another application of the empirical formula process. We will simply treat the parts of the hydrate, the salt and the water, as if they were elements like example 1 and example 2. So the first thing we have to do is convert the mass of the anhydrous salt after heating into moles, and then convert the mass of the water into moles. So first, identify the mass of the anhydrous salt. Notice that in the word problem, you are provided two masses, 45.00 grams and 27.86 grams. The 45.00 grams is for the hydrated salt. Hydrated meaning water is present. This salt with water attached to it is heated, and so the water is driven off and it leaves the container, and what is left behind in the container is the salt by itself. And now, because there is no water attached to that salt, it's referred to as anhydrous, and referring to that idea of negative or non, and hydrous referring to water, so no water with the salt. So the mass of the anhydrous salt is 27.86 grams. We need to convert this mass into moles. So notice I have the dimensional analysis process started, and we have 27.86 grams NaCl times mole divided by grams. So in our fractional relationship, when mole and gram are present, that means we need GFM information. However, this time, this is not an individual element, but it's an actual compound, so we have to calculate the GFM based on the elements present in sodium chloride. So looking at our formula, we have 1 Na, it contributes 23.0. We have 1 Cl in the formula, it contributes 35.5, and the summation of that is 58.5. So for NaCl, sodium chloride, 58.5 grams equates to 1 mole of this salt. So take this relationship and put it into the dimensional analysis. So we see that we have 27.86 grams NaCl times 1 mole divided by 58.5. Mathematically, since we have a grams in the numerator and the unit gram in the denominator, they reduce to 1, so we're left with only the unit of moles. Multiply numbers across the top, divide by any number down below, and we end up with 0.4762 moles of NaCl. Try to maintain sig figs. Our starting mass of NaCl, 4 significant figures. Therefore, I recorded the number of moles of NaCl also with 4 significant figures. So salt is only one part of the hydrate. Now we have to do the same type of math with the second part of the hydrate. Water is the other part of the hydrate. Think back to that idea in class where I stated that the sum of the parts equals the quantity or the value of the whole sample. So a hydrate is the whole sample. It's made up of a salt surrounded by a specific number of water. So if we take that idea and we put the information from the problem, we'll see that the hydrate has a mass of 45.00 grams, whereas the anhydrous salt has a mass of 27.86 grams, water should make up the remaining mass. So if you calculate the difference between the anhydrate versus the anhydrous salt, you will get the water's mass of 17.14 grams. So now we need to convert the 17.14 grams of water into moles. So the dimensional analysis I've got started. 17.14 grams of H2O times moles divided by grams. You need to know water's GFM. I asked you to memorize it, so you should be able to easily put it right in. So here we go. 17.14 grams of H2O times 1 mole divided by 18.0 grams. Grams reduced to 1. We're left with the unit of mole, and we have 0.9522 moles of water. Notice I tried to maintain sig figs. 4 sig figs in the mass of water, 4 significant figures in the moles for water. So step 1 is done, converting the mass of each part into moles. Second part is now we need to come up with the mole ratio. Second step, take a look at your calculated mole values, pick out the smaller one. So I hope that you realize that the number of moles of NaCl is the smaller mole value. Therefore, we need to divide both of the calculated mole values by the smaller value. Show your work, keep it neat. So you can see in the setup that the number of moles of NaCl and the number of moles of water are both being divided by the smaller mole value of 0.4762. The units of moles reduce, so mathematically the units reduce and we end up with a ratio. So since there is no more units, it's considered just a ratio. And on your calculator you should see that it works out to be 1 for the NaCl, and we get a number with lots of decimal points for the water. So I just try to think of this in the realms of sig figs. Since the mass of water, the number of moles of water, 4 sig figs, I think about keeping 1.999, but then the next digit to the right of the 9 is a 5, and it makes the 9 round up, and it's a continuous rounding, so my mole ratio ends up being a 1:2 ratio. So that means that in this hydrate, the salt to water ratio is 1:2. And with this mole ratio, here's a place of how we use it a little bit differently. These are not subscripts like we saw in example 1 and 2, but these become numbers called like coefficients that we place out in front of the chemical formula. So since it's a 1:2, you can see that a 1 was placed in front of NaCl, and where the N was in the original problem is now replaced with a 2. 1s, for the most part, we don't write in, so the best final hydrate formula is simply NaCl, big fat dot, surrounded by 2 H2O.